trying to get more people more excited about maths. And I do things like YouTube videos, which is where I suspect the vast majority of the young people are moving from, and I do BBC Radio 4, which is the rest of you. So I cover the whole spectrum. And so I recently wrote a book about Popeye, and I've written one book previously called Things to Make You Do in the Fourth Dimension, which, as mentioned in the introduction, is currently the second most viewed video on the RI channel, despite the fact that it's all abstract mathematics. And I figure tonight, with some applied mathematics, I'm taking number one. So I read the first book, and thank you for the book. Would you like to write a second book? And the problem with Things to Make You Do in the Fourth Dimension is, even though I was incredibly proud of it, and even though it sold very well for a maths book, it sold average for a book, which is great. My average is I'm above 50% of books. I'm very happy with that, right? But people don't care what's in the book, right? They can publish, another celebrity book or anything right now, actually. And so I had to convince them it was a good decision to publish a book about mathematics. And so I suggested to them I could write a book all about their favourite mathematics mistakes, which is where Humble Pie, a comedy of maths errors, came about. And they liked that because people like tales of disaster, they like stories of things going wrong, they enjoy laughing at other people. I made a career of being receiving into that, and so and they said, yes, write that book, it's great for people who are specifically maths nerds, which is therefore like way of describing my target demographic. Right? People still enjoy reading these stories, and my ulterior motive was by showing examples of where maths goes wrong in everything from finance, engineering, statistics, medicine, you name it. I can show the things you used to talk about, the maths that's required for these areas of our modern society, right? And so obviously maths works pretty flawlessly most of the time, so much so that most people have no idea how dependent we are on mathematics. We often don't value maths for no reason. So I think this is a great excuse to just talk about all the places maths is used, but by using things going wrong as my way in. And actually, because I used to be a maths teacher, actually, did you any maths teachers in? Hiding at the top, not sounding exciting, that's, you see, the hot term isn't it, right? Okay, so I used to be a maths teacher, just like 5 people cowering at the top of the room, and I left teaching, but I still remember now, a lot of young people, when you were at school, you're forced to do maths, right? You're forced to do it, because often perceived mathematics as a subject where you have to get it right. Getting the right answer is everything, it's the be-all, end-all of mathematics. And as a teacher, that's not always strictly true, right? Maths is about trying something and getting it wrong, and then trying it again, hopefully getting it less wrong, and then more wrong, and hopefully it converges in on the minimal amount of wrong possible. But it's a long, slow process of understanding it and not doing it well, and it's always very disappointing when students, or when people in standard issue humans are afraid to try some maths because they think if they don't get the right answer, they haven't done it correctly. And that's not true. If you get the wrong answer, you may still be correct in what you're trying it, right? Mathematics is about learning and teaching a very thing. And so I thought, how can I kind of bring that approach to what will otherwise just be a random collection of maths mistakes that have any real meaning? And I started with an inspirational poster that I had when I was a teacher. And the inspirational posters are the staple of the teaching rules when you decorate your classroom with. This was one of my absolute favourites. Education works best when all the parts are working. Now, let me just break this down for you. So, you've got cogs representing students, teachers, and parents. And the trouble is, when that big cog on the right represents students, if that rotates, let's say, clockwise, because it measures with teachers, teachers have to rotate anti-clockwise. That's all very nice. But neither are going anywhere because parents are jamming up the whole system. Surprisingly, more applaud from the teachers and parents. Surprisingly accurate poster in my humble experience, right? And then obviously people just haven't thought through the geometry of this situation, right? If you have cogs, they have to go clockwise, anti-clockwise, anti-clockwise. So in Manchester, were unveiling their new approach to public transport. They went with the classic three cogs making the city work together. Although people did point out and proceed to render in 3D. That's just this one point of view, possibly from the sides. It's fine. I said, well played. What you see is this, right? Look, that's neat. I think they were several steps ahead. Until I saw an article where President Trump in the United States was negotiating the North American Free Trade Agreement, and that was put in the newspapers to show how all the working parts of North America should be moving in unison. Please use this illustration. Well, you've already used your third dimension, right? You're not getting that back. So I paid money. I paid good money to license that image, to put it in my book, just so I could use the caption, "Making cogs great again." So, totally worth it. And then, finally, £2 coins. When the £2 coin came out to celebrate the millennium, there was a competition to decide this was the winning entry, and it's got different concentric, circles, bits, where it shows different stages of UK history. In the middle one, your kind of mechanical age here, is a series of cogs. And because if a cog goes clockwise, the one next to it is going to go anti-clockwise, then clockwise, anti-clockwise. You have to have an even number of cogs as you go around. The £2 coin has an odd number of cogs. It would not work. People on the internet were unimpressed and smug in equal measure. And the Royal Mint ran a statement saying that it doesn't matter, right? This is what you're going on about. It's just meant to represent that age. And I was like, that's curious, but I wonder, because it's a 50-50. I don't know what would be a great example of a similar 50-50 chance match, I think something, right? It could go either way. If you do it at random, you get an odd or an even number of cogs. And so I looked at the person who designed this coin, Bruce Russian, he's a teacher in Norfolk, and on his website he's got his original design, which worked. It's an even number of cogs. The actual coin that was made, these 3 cogs were removed, which meant that it wouldn't work. I said, wow, like he had it right, and the Royal Mint broke it. But was that deliberate? So I sent him an email. I said, I'm really sorry, I'm sure you'll find this out. I'm just curious, because I noticed you got it right. Was that deliberate? Did you think about it? Was that a concern? Well, I'm writing a book about math mistakes. I'm curious to know what was your thought process. And he replied to say that he didn't think, as an artist, it should have to be correct. He thought it's representative. A bunch of cogs, it doesn't make a difference to the artistic worth of the design. And to be honest, I quite agree with him. He then said that he decided to make it work anyway, because otherwise he would get loads of annoying emails from parents. I don't know whether it was involved, so there you go. So yes, he just thought, oh, we're going to complain, go on and on about it. And now this is the unfortunate edge, because when I was writing a book of math mistakes, I thought I was about niche theoretical math problems, of which there are things people thought they were something like that, and that's interesting to a small demographic like this guy. But then there's also the kind of pedantic wrong approach, things always said, oh, it's fine to make mistakes, which is one of the things I want to get across. And a lot of mistakes don't really matter, so I hunted down a copy of this book. I remembered this from years and years ago. I forget, I didn't have it as a child. I must have seen some, one of my friends, Gregory, and I saw somewhere this book where this is basically expressing his dislike of the possibility of being forced to live on the moon, which feels like a niche concern, but there you go. And I hunted down a copy of this book. I found it on the internet, and there's one thing about this which really warms me. It's not important, it's not a major issue. But anyone, apart from the China, very low activity over there, likes to tell what's wrong with it. Let's start where the moon should be. You are 100% correct. What are these? There's not a hole in the moon. As far as I'm aware, in the extended Sesame Street universe, there are not Muppet faces that we can see twinkling on the moon, right? And so you often see a crescent moon, and then you'll see stars shining through. And the moon is, from my point of view, a disc, right? And it's always there, it blocks out the stars. We just see different bits of paper constantly, and it's an artistic version of that. Bizarrely, I'm fond of that, right? But I'm like, they shouldn't show stars with a crescent moon, right? Anyway, but it's everybody. And then we have other examples, access to other small ones. And I'm looking at, separately, the license plates on the state of Texas. So this is a place in Texas, and as you can see, it's celebrating the fact that the shuttle was off Texas National Shuttle. There's not a bad angle, actually, for the shuttle taking off. It's finding that. It's already, it hasn't got any boosters or anything, so it should make its landing. I don't know, I was distracted by, over here, that star. That star is dangerously close to that. But the only way I could know for sure would be to somehow buy some license plates from Texas. So I did that. And they arrived in the post. There we are. This is actually genuinely, I scanned it. We got a low resolution version because it's online with 200 res. And if you zoom right in, and you fill in the rest of the moon, Texas. Undone by a lone star. So I was still happy to point out that maybe it's marking where the first landing site was, and it's very close. I might give them that to be entirely honest. But these properties, they're not. Okay, if we're just talking about are there practical implications of problems, in this case, don't get me wrong, I'm a big fan of getting maths correct and good maths PR and maths being important. But just practically, are they important? And sadly, in those cases, not really. But sometimes the maths can be important. So you may notice I am dancing around a very large Jenga tower. And I thought I'd have this set up through my show to artificially increase the amount of suspense for narrative purposes. So this is to show a fantastic effect about resonance. So this is a building, and we're going to show you in a second how a building resonates, hopefully to destruction. We'll see how lucky we get. Or unlucky, depending on what I'm trying to do at the time. Normally you will hear resonance discussed when it comes to bridges. And so there are a lot of bridges which have had resonance problems dating back into, I think the earliest one I've come across was in the 1800s up near Manchester, where Salford is now. There was a bridge and there was some troops marching over the bridge because they were all in step. They hit a resonance frequency of the bridge, and the bridge started to move, which apparently they thought was kind of fun. So they started singing a tune to match the bouncing bridge. Really got involved and they collapsed. And no one died. No one died. It's okay. It's difficult writing because you know when you cover engineering and medical mistakes, when I put the book together, like every second story, everybody dies. I can have a comedy book about maths, and every second, every 4 pages, and then everybody died. Right? So I think in all the engineering examples I'm going to give you, nobody died. I think in all the aviation stories in the book, nobody died. Don't get me wrong, people do die in aviation problems, just not the ones I put in the book. So that was the problem with the bridge in Manchester. In London, you've still got 40 years without the bridge. Troops must break step when marching over this bridge. That sign is still there. Troops are they must break step. Interestingly though, they must not break steps. Very difficult. And when I mention this, a lot of people are now thinking of one of two famous bridges. The Coman Narrows Bridge. This was a bridge in the US, Art Deco bridge, absolutely phenomenal, incredible amount of twist. Now, that's not your standard resonance from just skip marching on or quick bursts of wind, as you'll occasionally read online. This is resonating, but this is flutter. This is aerodynamic flutter from the wind coming up the valley. The flutter basically causes runway feedback. As the bridge came up, more wind pushed it higher up. When it finally bounced back down, more wind pushed it down, and you got this feedback which led it to go more wrong. So we finally decided maybe they should leave their car. You also, you've got the Millennium Bridge in London. This was opened in the year 2000. Now, if it was working randomly, it should be fine, because no, they're not going to match one particular frequency. But the footage, about 20% of the pedestrians, I mean, it's quite incredible, 20% of them were all marching in sync. The bridge is moving about 7.5%.
した時はそのもちろん忘れてません。そうですね。単にできるまだまだできるってこう言ってまさかのところあるみたいになってますね。はい。そういったことを気にかけてくれて、はい。そういう感謝してます。はい。まだまだ投げ続けろっていうことなので、みんなの思いに応えたいと、はい、改めて強く思いましたね。
Meters either way, right, which is about 7.5 too many. And so they had to close it and do all sorts of crazy things to dampen it. Because what was happening was the bridge was moving a bit, and people were moving with it, and so they weren't stepping in time with the bridge. So the bridge moving was causing the pedestrians to synchronise, and the pedestrians synchronising was causing the bridge to move. And you get this feedback. The official wording was it was synchronous lateral excitation. Right? If there was a feedback, energy was going in and it was matching a resonant frequency, which is of course totally terrifying. I'm more interested though. I've come obsessed with bridges one thing. They're easy to move. And for the most part now we get, which is why the London Bridge was so amazing. For the most part now bridges work fine. Buildings less so. So there was a building in South Korea in 2011, which is disturbingly recent. Anything within a decade I find terrifying. It was a 39-story building, and one day in 2011, people on the 38th floor evacuated because they thought there was an earthquake or something. It was shaking like crazy. They left the building. No one else knew what they were going on about. The building was fine. What? They did an investigation, and they recreated this, so this is genuinely true. It turns out on the 12th floor was an exercise class, and about 20 people. They exercised to Snap's I've Got the Power. If you're unfamiliar with Snap's I've Got the Power, that'd be better if it was a dramatic. If you're unfamiliar with Snap's I've Got the Power, and that's as much as I can play without the institution getting a copyright strike on their channel. So they danced that song. The song happened to match the resonant frequency of the building, and the 38th floor moved 10 times more than normal. Absolutely incredible. So when people design buildings, they have to try and factor this in, and there's a big problem, which is what this is actually kind of a teaching aid for learning about resonance in building. I borrowed this off a friend of mine who is an engineer, and they've actually come along to give me a hand because I'm not qualified to run this and see what it can show us about resonance. So can you please welcome to the stage from the University of Bath, Paul Shepherd. There he is. Welcome. I haven't seen you since we put this back together. Okay, it's been minutes. So don't get I get nervous. Okay, so first of all, what do you do at the University of Bath?
I teach mathematics to civil engineers. I research how we can use computers to design better buildings, and I've also got a role in our Institute of Mathematical Innovation, helping companies with their maths problems.
Fantastic. Don't have any started with maths to keep me happy. So you use this in your lectures, I believe.
Yes.
And just talk us through what is this for the kids?
Literally, it's a washing machine motor, but let's not go there. Literally, it's a washing machine motor in a box. There's some magic in the box. It causes the base to move back and forth, get that rate. And I have here a button that you're not qualified to press, and a dial to make it go faster or slower.
Can we? Is it like a safe slow? Can we?
We can do it really.
What do you want to leave? What do you want to do? Okay, here we go. So we can do it slow. We show it and it still work.
I'll catch it if it's really slow, yeah? Like, you know,
that is fantastically slow. If anyone starts watching the video right now, they're like, it's playing at the wrong speed. Still awake. So that's it, right? And on top of this, we've got a Jenga tower. Yeah. And what we want to demonstrate with this is that if you hit the resonant frequency of the Jenga tower, it will fall over. But to make it a challenge, first we're going to start with frequency where it won't fall over. So we think we found one. We're unconvinced. We put it back together and went, now it's slightly different. And we'll have a slightly different resonant frequency. Let's give it a go. So should we slam straight into the range of
right.
Yeah, I'm going to catch it just in case we get unlucky.
If you get unlucky, it goes that way.
Oh, yeah, right. Here we go. It's fine. Look at it. It's fine. We're happily living in that building. So we've got it moving at quite a frequency. It's shaking. Don't get me wrong. It's shaking it all over the place, but it's not falling over. What we're going to do now is we're going to keep the amplitude the same because we can't adjust it, and we're going to reduce the frequency so we're shaking it less. So do you want to reduce the frequency? Just slow the frequency down. So now, if you stand back, there's now less shaking. Sorry. Wow. Now I feel confident. Less shaking, and in theory, even though we're shaking it less, if we hit a resonant frequency, it will fall over. I think we're near one. As we're shaking it slower, we're putting less energy into it. We were just putting the energy in at just the right time to build and accumulate in the system rather than cancelling out. And so you show this to what? The civil engineering students?
Yes. We don't want that to happen to buildings, and there's a certain number of things we can change to the building to make sure that the frequency at which it would do that is different from the frequencies that it would see in its daily life. Okay, so we kind of tune the building away from.
And you don't test it by putting models on this?
No.
You run like simulations or something?
We do maths in it, obviously.
Correct answer. And are there any buildings, like, can you give us examples of buildings you've done this on, or are you like under a lot of non-disclosure agreements?
Not anymore.
No, you're an academic now.
Well, I was working on a bridge I won't say which one, at the same time as the Wobbly Bridge across the Thames had problems. So I was working for, let's say, a different company, and of course we watched that and thought we'd better make trebly sure that we're not.
You're like, whoops, that happened to them first.
So, I mean, it did take the world of engineering a little bit by surprise, but it happened so obviously. So, yeah, we can now understand. It was the person element that we knew the maths, but we didn't quite understand how people synchronize better than unpredictable.
And now, in the 2 decades since, when people design bridges, or any building, I guess, do you have to now factor in human movement as well?
Yeah, after that happened, a lot of people did a lot of experiments and research to work out how it happens and to quantify it, and now that's what new research is taken into account when we design bridges today.
Fantastic. Maybe a huge round of applause for Paul Shepherd. It's literally just out of it now. Okay, so, but his mic has been turned off. Okay, right. So I think it's right because the thing about engineering is we're often building things beyond our current full mathematical understanding. Right? We use maths to build things which no longer make sense intuitively. Because if you look at something like the Millennium Bridge, you can't just go, that's all that. Indeed, most of the perfect built these stable buildings, before we had computers and advanced maths, we built them out of massive bits of rocks where you can look at it and go, yep, that's not going anywhere. Right? Whereas now we need computers and mathematics to check. And occasionally things go wrong. We will forget about a factor, or there's a new bit of mathematical behaviour will emerge, and then the engineering industry learns, improves, and the maths is developed, and we carry on building more and more ridiculous things. Okay, so I'm going to leave these here and you carefully dance around them. What I'm going to do, because I've got one more guest at the end who's got something else I want to show you, but between now and then, I had so many stories, because I had hundreds and hundreds of stories, of which a couple hundred made it into the book, and I couldn't decide which ones I was going to show you here today. So what I thought I would do is pick them at random. So I have here a spinning wheel, and so what we can do is, if we spin the wheel, right, it'll settle on the colours. This is not it, we'll do it again in a second. So we get a colour, and up here I've got a breakdown of what the colours mean. So we would do a story about programming, right? Boom, programming story. I get a programming story on the laptop, we do it, we have a great time, we do this a few times, then we bring on the fun guest. Very straightforward. So I'm going to get some volunteers to come down and, no, not yet. You haven't heard all the rules. I think I'm going to do this 3 times. That's my guess, 3 times. And so my plan is, if we have 3 different volunteers, we will start with a very young volunteer, we will then have more of a teenage high school volunteer, and then we'll have an adult volunteer. So if people watch this quickly, or it's edited down, and we'll have the one volunteer aging rapidly throughout the talk. Okay, so are there any... Wait, the sentence. Any young volunteers would like to come down to me first? Over there. All right, give me a wave. You get a round of applause. Come on down. Hi. Very nice to meet you. What's your name? Mario. Mario, nice to meet you. Just come over here, Mario. So you can see I've got my spinner here. What I'm going to do is to grab one of these and just give it a real spin, and we'll see which of any of the colours it ends up on. Up you go. Good spin. Whatever colour it is, just say the category nice and loud. Oh, it's just in green. What's green? Thank you very much. Give it a round of applause. Give me a second to find my probability slides. There we go. Okay, so we're going to start with a tale about probability and how humans are bad at probability. And this is one of my favourite examples, where we can try to scam someone, right? We can try and trick someone into thinking it's a fair game when actually it's not. So for this, I need a volunteer. However, I'm going to take one from someone right up the top. Is there anyone? Because you don't have to come down for this. You remain completely in situ. Let's go with first over there, leaning on the right. That's back. Yep, give me a wave. Thanks. What's your name? Very loud. There we go. Here. Okay, so what we're going to do, right? We're going to flip a coin down here. It's going to be heads or tails, right? And you're going to try and predict if it's heads or tails. Has anyone down here got a coin? Any of the adults got a coin they're prepared to flip for me? So are you happy to be a coin flipper? Okay, you can say that you flip the coin very straightforward. Okay, right. So what we're going to do is flip the coin. You're going to predict, would you like heads or tails? You feel like this is going to be a double-sided coin. I feel like we're having more of a conversation than I expected. Let's have a look. Give me the coin. Oh my goodness. Okay, ready? Who would you like to verify the coin? Pick a human. The one next to you. Pick a human who's closer to me than you. It's okay, I've got a solution, don't worry. Would anyone like to know? Okay, who? There. That one. Okay. Can you have a look at that? Is it a head on both sides? No, it's a tail on one side. Excellent. Wow. That was anticlimactic. Here you are. You are now deemed trustworthy. By simply saying either the word heads or the word tails. What do you think it's going to be? Tails. Okay, everyone in your own mind decide what you think it's going to be. Okay. Flip it and then call it out nice and nice. Good flip. Solid flip. What is it? Tails. Who's right? Hands up if you're right. Okay, up here. Hands up if you're wrong. Okay, slightly more because, adorable kids. Okay. So, was that fair though? And it's not a trick coin, there's nothing fancy going on, it's not because there's more metal on one side than the other, right? Assuming that it's a perfectly fair coin, everyone should be happy, that was a perfectly fair challenge. In fact, if we were to bet money, which young people you shouldn't, right? But were you to do such a thing, you would have a 50-50 chance of winning versus losing. And if you played over and over again, you would win as often as you lose. If you played the same person, you would end up passing money back pretty much at random, right? No one has an advantage in that game. We can make the game slightly more exciting by having more than one flip. So if instead of asking you what one flip would be, I could say, we're going to flip it, we'll do 2 flips. So you can choose heads, or heads, tails, or tails, heads, or tails, tails. What would you like, actually? What would you like? Right? And everyone here could think of their own one that they want to have, and if we flipped it, you've all got a 1 in 4 chance of being right. Or if we're playing 2 of us, if we don't get it straight away, we will keep flipping it until one of us has our run come up first. Still a fair coin. Must be still fair. What if we did 3? In fact, everyone in your own minds decide what 3 flips in a row. Heads, tails, heads, tails, 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 heads, tails, tails. Right? In your own minds, decide what you think it's going to be. What did you size up there? Tails, tails, you get 1 more. Heads, tails, tails, heads, right? In fact, there you are. There's all the options. So you may have picked one of those, and they're all equally open. I'm now going to bet all of you simultaneously that mine will come up before yours. So I want you to have a look at this, and I want you to choose which one is yours. Make sure you choose which one is yours, and then I'm going to add my predictions next to yours. So if you predicted heads, heads, tails, I predict tails, heads, heads. So I'm playing you all individually. If you pick tails, tails, heads, I pick heads, tails, tails. I have different predictions. I mean, some of them are the same, but I mix up the predictions based on what you said. So everyone make sure you're happy. Which one is yours, and my prediction next to it. You all got that? Okay. So what we're going to do now is we're going to start flipping the coin until either you win or I win, and we'll keep going until every single game is finished. So, first one up. Flip the coin. Where do we go? Heads. Second one. Oh, third one. Tails. So, a lot of people are now happy they've just won. If you said heads, heads, tails, you have just beaten me. I said tails, heads, heads, which has not come up. But some people, yours isn't here yet. So, flip it again. Great, I love it. You're being more enthusiastic each time. Tails. So now, the last 3 are now heads, tails, tails. So if you have heads, tails, tails, you've now won. If I had heads, tails, tails, I've now won. Or if I had heads, tails, tails against yours, I've now won. You need to keep track who wins first, you or me. So if either I beat you with heads, heads, tails, or I beat you with heads, tails, tails, it's better than mine. Okay, give us another flip. Heads. So the next one is tails, tails, heads. Tails, tails.